right? So this is a design example. The critical stress intensity factor of the material is known. How do they know it? We'll see later on. Now in design B, they say there is a largest flaw which we detected, a very large flaw, really 9 millimeter is a very serious matter, and the failure stress is 112 megapascal. Okay, so they are saying that use this equation, that critical stress is Kc upon Y, so this is there. Okay, the key point, Y and Kc are the same in both designs, but let us see. Now let us go to design B. Use the same material, material is the same, so it's this value is the same Kc, but the largest flaw is 4 millimeter. So what is the failure stress now? Okay, remember now here in design A we were saying that the critical stress intensity factor of the material is known and the largest flaw is 9 millimeter. So applying the theory that you had earlier, you found from this equation, you know the Y of the crack, you know that this is 9 millimeter, pi is known, and this is known. So therefore we found that this value is 112 megapascal. So this was one design, that if my material has this stress intensity factor, right, and if the maximum crack size is 9 millimeter, then at 112 megapascal of applied stress, this material will fail. So as long as the applied stress is less than 112, we are safe. In design B, we are now saying it is the same material, but now the largest flaw size is 4. So what is the failure stress? So we can put in the same equation, or we can now do this, that you see this is one design, this is the other design. So, right, so sigma C, multiply this there, take this there, take this there. So Y pi A max will be the Kc, right? Now Kc is the same, material is the same, isn't it? Material is the same, but the A max has changed. So Kc is equal to sigma C Y pi A max. Okay, so we take it there. Now we remove Y also because it is the same material. So for the time being, remove Y also. So sigma C into pi A max, sigma C pi A max. This is for case A, and this is sigma C pi A max for case B, because this equation is Kc value and this equation is also Kc value. So they have to be equal because the material is the same, it has the same Kc. So just applying it here, you can now find that the sigma C for B, sigma C here was 112, sigma C here is 168, right? 168. So without knowing the Kc of the material, you can find it like this. But otherwise you could do like before, only that the Y was not known. Therefore we had an issue that Y is not, but Kc is known, and A max had changed. So but what do you find out from here? You see, the result is that if there is a 9 millimeter flaw, then it will fail at 112 megapascal. If it is a 4 millimeter flaw, then it will fail at 168 megapascal. Does it make sense? Just think. It makes perfect sense. You see, I am trying to apply some load on a certain material. I have selected the same material, so the resistance to fracture of the material is the same. Now if the existing crack size is small, then it will take a larger force to crack it. But if the existing crack size is large, it will crack at a lower load. So yes, when the crack size is 4 millimeter, it will need 168 megapascal to crack it. But if the crack size is 9 millimeter, it will crack only at 112, much lower than that. So it does make sense. But now this result that you are giving is totally brand new, right? This is material science and solid mechanics based on pre-existing cracks in the material, not based on the assumption that the material is flawless. So let us take an example now. Uh, a relatively large plate of a glass is subjected to a tensile stress of 40 megapascal. If the specific energy and modulus of elasticity for this glass are 0.3 joule per square meter and 69 gigapascal respectively, determine the maximum length of a surface flaw that is possible without fracture. So you see, you should now start feeling big. This is your first problem of fracture mechanics to solve, right? Not based on earlier material science or earlier machine design and so on, but the first time that if there is a crack and so on, then how do we do design calculations and so forth. Now, if you remember my previous courses, there are 2 or 3 things I always tell you. I'll repeat it again and again. The best way to learn, even if there is a solved example, is to read the problem and hide the solution. Never read the solution, please, in any course, not just this course. Just like I have done for you, I have written only the problem here. I could have shown you the full solution straight away. But that is important, that you read only the problem and hide the solution anywhere in any course. If you do that, your mind works and gets challenged and you learn a lot. But if you just simply read the solution, then you feel that it is very simple, because it is. But then if the instructor changes the problem a little, slightly only, then you are lost, because you don't have worked yourself. So in every course, please do this, right? Of course, you have the access to the PDF lectures, so you can turn back any page, but don't turn any page in the future, otherwise you will make yourself weak, okay? So just go back and so on. The other thing is, if you remember, I always tell you, whenever there is a problem, then do first what? Read it carefully. Second step, write the knowns and unknowns, always. So in this problem, your known is that there is a known stress sigma of 40 megapascal. There is a known gamma S surface energy of 0.3 joule per square meter. And there is a known Young's modulus capital E of 69 gigapascal. And the length of the surface flaw A is the unknown. So this is it. Sigma known, gamma S known, capital E known, small a is unknown, right? So read the problem, understand what they are saying. If it is glass, it is a brittle material, right? There is no assumption. It is glass. Glass is a brittle material. So it means that if the theory was developed for brittle materials, it is totally applicable. Otherwise, if it was a ductile material, then the solution that we find from here will be approximate. But you know that it is there. So now go ahead, pause my lecture, take your pen and paper, and it should be the pen and paper on which you are making the notes for the whole course, so that everything is in record for you. So take that pen and paper, pause my lecture please, take down the knowns and unknowns and solve it, please. So now when you are listening to me, you have removed that pause. It means that you tried your level best to solve it. It is a simple problem here, of course. And once you solved it, then you are listening to me, right? So now tell me, in the previous few slides, what were the new equations that you got for fracture mechanics theory? You see, we started with Griffith's theory of brittle materials, isn't it? Griffith's theory of brittle material, where there was the applied stress, and there was A, the crack size, and there was gamma S, the surface energy of the material, and so on. That was one equation, and we talked about it in different ways. Then in the previous slide, there was a new equation of the stress concentration factor K in terms of some property of the crack called Y, and the applied stress sigma, and the crack size A, right, and so on, right? So these are the only two equations. You can go back, look at my lecture notes again, right? Don't go forward. Go back in the previous few pages in my lecture notes, and you see that these are the equations. So now the data that you have taken, it fits which of these equations, and then solve it. So now let me share the solution with you, but you have most probably, all of you, already arrived at the correct solution. So this is the problem, right? This is the problem. So I have already done what you do. Sigma is 40 megapascal, gamma s is 0.3 joule, E is 69 gigapascal, A is unknown. So this is the equation. This is the Griffith equation. Sigma C is 2E gamma s upon pi A, right? So just rearrange it, square it, this becomes a square, that root sign goes away, A will go there, so this equation will become this. A is equal to 2E gamma s upon pi sigma square. So read the question, write the knowns and the unknowns, look at the equations available and rearrange. Once you have everything here, now this is an equation which will tell you the crack size A. So now only one thing, go back to the basic units for everything. E is in gigapascal, so write 69 into 10 raised to 9. Sigma is megapascal, so write 40 into 10 raised to 6. Gamma is directly simply joule meter, which is basic unit. So any problem, if it is an inch pound system, convert every foot or other thing into inch, convert every kilo pound into pound, and then solve it. Here in SI system, convert every megapascal or gigapascal into basic units and then solve it. So if you solve it, then your result was 8.2 into 10 raised to minus 6 meter. So now you can write it directly. If you leave it here, it will be bad, right? We don't leave it like this without the standard units. So if you leave it like this, this is 8.2 micron, 8.2 micrometer, micron, or convert it into 0.0082 millimeter. So this and this are acceptable answers. This is mathematically totally correct, but not acceptable as an engineer, right? So this is not very nice. Okay. So this is it. I will leave you here for now, and in the future we will continue inshallah, and please make sure that whenever you solve any problem, do this strategy, that read the problem carefully, write the knowns and unknowns, select your equation, solve it, and when solving it, then please make always the basic units, right? Otherwise, if you leave it at 8.2 into 10 raised to minus 6 meter, then it may not be something very nice. Okay? Thanks a lot. I'll see you in the next lecture, inshallah. Remember that this is the first lecture of chapter 1B. I divided chapter 1 into 1A and 1B. So this is lecture 1 of chapter 1B. We will continue it further. And remember that before the next time, before the next lecture is due, if this is Sunday, then the next lecture is due on Tuesday. So you have only today and tomorrow to solve it. And please solve it then and submit it. This is very simple and it will improve your understanding. Thanks a lot. Ma salama.